Because we know that thermodynamics fundamentally deals with the transfer or conversion of energy, we can first remind ourselves of exactly how energy is defined. We know that energy is the capacity to do work or to transfer heat. All forms of energy are either kinetic or potential. The total energy in a system is going to be the sum of all potential and kinetic energy contributions. So energy total is equal to the sum of the kinetic energy plus the potential energy. So breaking that down just a little bit further, we remember that kinetic energy is the energy of motion, and it is defined as 1/2 of the mass of an object times its velocity squared. That mass is given in a unit of kilograms, and the velocity is given in a unit of meters per second. And so from there we get our energy unit, which is joules, kilogram, meter square per second square. On the other hand, we remember from physics that our potential energy is the energy that an object has by virtue of its position. We say that if we take, for instance, a ball resting on top of a hill, that ball has the greatest potential energy as the height increases. The greater the height that an object has to fall from, the greater the potential energy. So as this ball falls down the hill, its potential energy becomes smaller and smaller. When we're talking about chemical potential energy, we are talking about the potential energy that is stored in a chemical substance by virtue of its bonds, atoms, and electrons. So we're talking then about electrostatic energy. So for a chemical entity, in terms of chemical potential energy, we're talking about two charges that are separated by a distance d. So these are charges of the atomic particle, and this is the distance that separates the two particles. My stylus is writing a little bit wide, so this is distance between two particles. And these are charge 1 and charge 2, charges of 2 or more particles. Since we know that the total energy of a system is composed of the sum of the kinetic and the potential energies, and we know that based on the law of conservation of energy, total amount of energy in the universe is constant, and energy cannot be created or destroyed, only transferred from one form to the other, then energy therefore is interconvertible. Kinetic and potential energy are interconvertible. So basically, that tells us that the law of conservation of energy states that the total amount of energy in the universe is constant. That when we talk about the energy that we get from a system and the internal energy that we consider for the surroundings, that it can be interconverted back and forth between a system and its surroundings, but no net energy increase or decrease. Energy is constant. So, that is the law of conservation of energy. And so, the first law of thermodynamics then states that energy can be converted from one form to the other, but not created or destroyed. And our mathematical representation tells us that as we lose heat or work or a sum of the two, as we change the internal energy in the system, then an equal and opposite change of internal energy is occurring in the surroundings. So just to put into perspective how much a joule is, which is our basic unit of measuring energy, just to put that number in, that unit in perspective, this little slide here just tells us about how much energy is expended or is involved in different processes. Anything from down here on the lower end, which is how much energy we would expend in typing one key on a typewriter, all the way up to how much energy we consume on a daily basis to sustain our bodily functions, all the way up to a hurricane and an atomic bomb. So you can kind of get an idea of the orders of magnitude that we would expect from different processes. Sorry, I need to go back. So we have talked about the first law of thermodynamics. We have talked about the fact that energy is transformed between heat and work. We have talked about that the internal energy of the system deals with all of the kinetic and potential energy contributions of that system. We have talked about the law of conservation of energy, and we have talked about how it gives rise to the first law of thermodynamics. So, since we deal with developing mathematical identities and relationships in PChem and all other forms of chemistry, many other forms of chemistry, then we want to actually write out what is our mathematical way of stating the first law of thermodynamics. The first law of thermodynamics, mathematically stated, tells us that the internal energy of a system is equal to heat plus work. In an isolated system, which means that a system that is not able to exchange matter or energy with its surroundings, there is no change in delta U. Delta U would be 0. Therefore, the heat and work can be exchanged back and forth, but the overall change of internal energy will be 0. And so basically, that's a way of saying the mathematical equivalency of the first law of thermodynamics, which says that the internal energy of an isolated system is constant. So what are the reasons why we care about the first law of thermodynamics? Why do we care about understanding internal energy and the interconversion between heat and work? We care because when we are chemists, we want to know information about physical processes and chemical processes. We want to know, in a reaction, will molecules form? Will that reaction occur? And if it does occur, how fast? What direction will a reaction have a tendency to go in? There are many fundamental questions that a chemist can gain answers to, basically from the fundamental concepts of thermodynamics. So we know that the internal energy of a system is equal to the sum of the heat and the work possessed or not possessed done by that system. And coincidentally, heat and work are not energy. They are not forms of energy. They are ways of transferring energy from one form to another. So energy can be exchanged through a system by either heating it or doing work on it. When a system is heated, energy exchange is exchanged from the surroundings to the system, or from the system to the surroundings as heat. When a system does work, anytime we're thinking about something that does work, the thing to do is to consider it raising that system, changing the height of a weight or an imaginary weight in the surroundings. An example would be the expansion of a gas. As that gas is expanded, we can imagine that it is pushing against an external weight in the surroundings. So when that type of scenario would occur, then that is when we can know that work is being done. So if there is a temperature difference from the system and the surroundings, then we know we have a transfer of heat. Remember when we talked about the situation of the thermal equilibrium is when we have two bodies that are put together that are at different temperatures. The heat will flow from the warmer body to the colder body until the temperatures are equal. Anytime you have two bodies or two objects in contact with one another and they're at different temperatures, then heating will occur, because the temperature, the heat will have a tendency to flow from the warmer body to the colder body until those temperatures are equal. So we've said all that, and basically we know that a takeaway message from what I just said is that the internal energy of a system can be changed either by doing work on the system or by heating it. We know that if we want to ask ourselves, has work been done or has heat been transferred? If there has been a net increase or decrease in temperature, then there has been a transfer of energy as heat. And if there has been a imaginary height that could have possibly been raised in the surroundings as a result of a process, then we know we have a situation of work being done. A quick illustration of this is to consider a chemical reaction. And this shouldn't be here. Let's move this around. All right. Let us consider the reaction of zinc solid. We'll use this little pile of powder that I'm trying to draw here to represent zinc solid that we put in a reaction vessel. And then let's say we've got a Erlenmeyer flask that contains some hydrochloric acid, HCl. And let's say that this is the product reactant side, this is the product side. Alright, so now I'm going to let this reaction occur. We're going to empty our Erlenmeyer, we're going to turn it upside down and pour out the hydrochloric acid. and we're going to notice what happens as that reaction proceeds. We're going to form zinc chloride down here, aqueous, which means that zinc chloride in a solution of water. But as we do that, we're also going to form H2 gas. As we form this hydrogen gas, we will notice that we said if we have an imaginary weight here that we consider, and when we do something like this in a lab, we're talking about, just think about the surroundings, like for example the coffee cup calorimeter that we use in our lab. Just consider a beaker or a cup. You can't see a barrier there, but if you consider that as that gas is expanded, the atmosphere that is in contact with this vessel is being pushed back by the generation of gas. So therefore, that is equivalent to thinking about there being a weight risen in the surroundings. So if that type of activity takes place, then we will know that work has been done. So in this particular example, we know that we have done work because we've liberated gas, and we know that as we generated that gas, that it has pushed back on the atmosphere, and we could consider that atmosphere of being a weight on a frictionless piston. On the other hand, if we wanted to find out whether or not there was a transfer of heat during this reaction, we could have conducted this reaction in a container of ice, for example. We could have had a thermometer, a container of ice, a water bath, or something that we could measure the temperature of. We could have measured the temperature of this bath both before we let the reaction proceed and after. And if there is a temperature difference from before the reaction occurred and after the reaction occurred, then we know that we have had either the generation of heat or the absorption of heat. So we have had a heat transfer. If we do this reaction on a scale where we isolate the system to where we do not allow a heat transfer, and we do it under adiabatic conditions, which are conditions that do not allow heat transfer, then all of the energy produced by this reaction would be in the form of work. So, this slide was simply to show that in a chemical reaction, we can determine whether or not heat has been done by considering whether or not an imaginary weight in the surroundings has been raised or lowered, and we can consider if that reaction has done heat, has transferred heat by measuring the temperature before the reaction takes place and after. And if there is a change in temperature, then there has been a transfer of heat either into the system or out of the system.